Hi. So we have just explained the Keller theorem, which says that every group is isomorphic to a group of permutations. We have proved that, and we have also given an example now that the how to construct the permutation group, given that you have already a group. Okay. Now we will talk about the properties of isomorphisms. Perfect. So we give a long theorem which has 7 points. Says that theorem 6.2. So these are the properties of isomorphisms acting on elements. Okay. The statement is suppose that phi is an isomorphism. Phi is an isomorphism from a group G onto a group G bar, then 1. Phi carries the identity of G to the identity of G bar. That means phi of E is equal to actually equal to E bar. Something like that. E is an identity of G. 2, for every integer n, for every integer n, and for every group element A and G, phi of A power n is equal to phi of A power of phi of A. Okay. 3, for any elements A and B of the group G, and A and B commute, A and B commute if and only if and only if phi of A and phi of B commute. So if G is an abelian group, then G bar should be an abelian group. That's what it is saying. Okay. 4. If G is cyclic, generated by an element A, if and only if G bar is generated by an element phi of A. Right. 5. Order of an element is element A of the group G is equal to the order of an element n g bar for all phi of a. The order of element phi of a n g bar for all a in G. You can say if isomorphisms preserve orders. Number 6. For a fixed integer k and a fixed group element b in G, the equation x power k is p has the same number of solutions in G is does the equation x power k is equal to phi of p in G bar. If an equation is solvable and has roots in G, then the equation is also solvable and has roots in G bar. Preserve solutions, you can say. 7. If G is finite, then G and G bar have exactly the same number of elements of every order. Perfect. Now we can actually give the proof for all of these properties, and it would not be very difficult, but we can just say few things about that isomorphisms preserve identities and maps them from one to another. Orders of the elements also preserved can be also be preserved and mapped from one group to another group. And number 3 says if you have two elements which are commutative, which commute in G, they can only commute if the corresponding elements in G bar commute. Right? So property 5 follows from the property 1 and 2. Property 6 follows from the property 2, and property 7 follows from the property 5. And we can try and proving them somehow. So let's give a rough proof. Let us denote E, the identity in G by E, and the identity in G bar by E bar. Then, since E can be written as E into E, we have phi of E is equal to phi of EE, which is phi of E into phi of E, right? Also, because phi of E belongs to G bar, we have phi of E is equal to E bar phi of E as well. Thus, by cancellation, E bar is nothing but phi of E. Okay, this proves one.
For positive integers, property 2 follows from the definition of the isomorphisms and mathematical induction.
So you can write 1 here, and then you can say 2 here. So by mathematical induction and definition of isomorphisms, if n is negative, negative, and minus n is positive, and we have from property 1 and the observation about the positive integer case that from 1 and the observation about the case, positive integer case, integer case that E is phi of E, which is phi of G power n into G power minus n, which is phi of G power n into phi of G power minus phi of G power minus n. Thus, multiplying both sides on the right side on the right by phi of G power n, we get or we have phi of G power n is equal to phi of G power n. And then for property 1 takes care of the case when n is 0. So that's it. Okay. Now for 4, we say that late G is generated by the set A, the element A, and notice that by the closure property, you can generate phi of A is equal phi of A is going to be the subset inside G bar, because phi is onto for any element P in G bar. There is an element A power K in G such that phi of A power K is equal to B. Thus, B is nothing but phi of A power K, and so B belongs to the state generated by phi of A. This proves that this proves that G bar is generated by phi of A. Perfect. That is 4. Now we have to show the other way around. Now suppose that G bar is generated by phi of A. Okay. Now clearly A is the state generated by A is a subset inside G for any element B in G. We have phi of B as an element inside state generated by phi of A. Okay. So for some integer K, we have phi of P is equal to phi of A power K, which is nothing but phi of A power K, because phi is 1, 1, 1 to 1, 1 to 1. B should be equal to A power K. Now this proves that the state generated by A is nothing but actually equal to G. And that completes the proof for the theorem, because we have said that phi follows from the property 1 and 2, 6 follows from the property 2, and 7 follows from the property 5. And that's it. Okay. Perfect. Now let's give another proof, another theorem, and that will also give us some properties of isomorphisms. So that theorem says that is theorem 6.3 says that these are the properties of isomorphism acting on groups. Okay, the statement is suppose phi is an isomorphism from a group G to a group, let's say, onto a group G bar, then number one is phi inverse is an isomorphism from G bar onto G. Two is if G is abelian, if and only if G bar is abelian. Three is G is cyclic, if and only if G bar is cyclic. Four is if K is a subgroup of G, then phi of K given by phi of small k, given that such that small k is an element inside capital K, is a subgroup of G bar. Number five is if K bar is a subgroup of G bar, then phi inverse of K bar is given by G into G, given that phi of G is an element inside K bar, is a subgroup of G. And number six says phi, phi of the center of G is equal to the center of G bar. Perfect. Now, these theorems we won't be able we won't be proving this theorem, but we'll now talk about the consequences. So theorem 6.2 and theorem 6.3 provide ways to prove that groups G and G bar are not isomorphic. Because if one of the things broke, then the other one doesn't follow. That is, you can say, observe that order of G is not equal to the order of G bar. Second, observe that G or G bar is cyclic and the other is not. Right? We observe that G or G bar is abelian, and the other is not. 4. Show that the largest order of an element of any element in G is not the same as the largest order of any element in G bar. So show that the largest order of any element in G is not the same as the largest order of any element in G bar. Okay. You can also say that show that the number of elements of some specific order in G is not the same as the number of elements of that order in G bar. Those are the ways you can actually say that there is no isomorphism given between two groups. Perfect. Now, using these five, we can give examples. Let's say we have example 9, which says that we have groups of order 12, that is Z12, D6, and A4, alternative group of order 4. The largest order element in these have the largest order of elements in these is 12, 6, and 3, respectively. So, no two are isomorphic. Alternatively, the number of elements of order 2 in each is 1, 7, and 30, and 3. Alternatively, the number of elements of order 2 in each is 1, 7, and 3. Okay, now example 10 says the group Q of rational numbers under addition is not isomorphic to the group Q star of non-zero rational numbers under multiplication. So let's say we have G, a group which is Q under addition, and we have the group G bar, which is Q star, which is nothing but Q minus 0 under multiplication. Okay, and so G and G bar are not isomorphic, because every non-identity element of Q, every non-identity element of G has infinite order, infinite order, is nx is equals to 0 if and only if n is 0, right? Or x is 0, or x is 0, right? Whereas minus whereas in G bar we have -1 is have order 2. So we have few elements which have different orders, and that's enough to show that the groups are not isomorphic. Perfect. Now, theorem 6.2 and 6.3 shows that the isomorphic groups have the many properties in common. Actually, the definition is precisely formulated so that isomorphic groups have all group theoretic properties in common. By this, we mean that if two groups are isomorphic, then any property that can be expressed in the language of group theory is true for one, if and only if it is true for the other. This is why algebraists speak of isomorphic groups as equal or the same. Okay, now these are group equivalent. Perfect. Thank you so much. Bye.